Well, hi guys. This is going to be a course teaching you how to program, basically, how to code. If you've never really coded before, this course should get you started on that. Or if you've done some basic coding, this will definitely help you as well. It might be a good refresher on some of the very basics. But yes, I'll be covering some of the basics you need to be able to go through your programming career, well, even if it's just a project, but what you actually need at the end of the day to be a good programmer. It's very important to stress that you do need to go to the fundamentals of programming. A lot of people don't go through it and then struggle later on in their programming ventures. So we're going to be starting at the very bottom. We're going to be looking at the bits and the bytes. And we'll be taking it all the way through to, we'll be investigating a couple of languages, but mostly we'll be concentrating on C# development, and we'll be doing a command line application in C# and as well as a Blazor application for websites using WebAssembly, and we'll also be writing a .NET DLL, dynamic link library, so that you don't have to keep all your code in your executable itself, but you can split the code logic up amongst multiple files. I know this is pushing it a bit now, considering this is the very first video in Introduction to Programming. So maybe let's get down to it. Let's just start at the absolute basics and firstly define what does it mean to program, to write a software program. It is important to remember that computers are basically well, it's hardware. You get hardware and software, and hardware is basically the physical devices which you can feel of a computer. Like you can feel your CPU, you can feel your monitor, you can feel your keyboard, your hard drive, your USB, and so forth. Whereas software, which is used to communicate with those hardware devices and make them do something, like have your video screen show an image, you know, if you're playing a game or whatever, if you press a key on your keyboard, so the computer actually knows what key you pressed. Did you press the X or Z? So you basically, you split there between the actual hardware and the software. And the software controls the hardware, and the hardware inputs information to the software. The software basically is not something tangible. You can't well, you can hold a program. If it's, for instance, on a hard drive, you can pick the hard drive up, and on the hard drive is the program in magnetic form. But that's not exactly what, you know, that's not really true. You're not really holding a software program. You're just holding a hardware device that's got magnets on it. But that can be interpreted by the computer. Those magnets, those poles, the north and south poles, can be interpreted as a program. And that's basically what you see when you see in the movies and so forth. If some hacker's been doing some coding, and they show it to you on the screen, all those fancy words and stuff that's written up there, that's a software program typically. And all it really is a conceptual, it's an idea that's captured. Let's say on paper, like a novel, you write a story, you capture the actual words on paper. The book itself contains the novel, but the book isn't the novel. So holding a hard drive is not holding a program. The program is merely the concepts that you captured in some electronic format that can be read back later and replayed, and then to affect hardware or other bits of software in some way. Okay, so now still on the hardware side of things, basically everything comes down to bits. Computers are what they call binary systems, binary for 2, and the reason why they've chosen that term is because the way that commands and so forth are sent through a computer itself. So in other words, the way the software that you write is actually interpreted by the computer is in a binary format, using typically magnetic fields or electric voltages and so forth. So a very good example would be, for instance, the electric voltage that's flowing through your processor or your entire system as such. In a perfect scenario, it would be basically what I'm showing you here as a square wave. Assume that is the electric voltage. That's the actual waveform coming flowing through the system, and that is now the ideal situation. So the way that the engineers designed a processor is that these different voltages, the high and the low voltages, since you can have a high or a low, that sort of defines a binary system. And therefore you can use that to represent zeros and ones, which is what all programming uses. And all commands in a hardware system uses those binary commands. So in this example of the square wave here, for instance, we start with the square wave above the x-axis, and that can be assumed to be a 1. Then right after that it drops below the x-axis, which is a 0, then above again a 1, and then a 0 down again, and a 1 again. So that square wave there represents to us a 1, a 0, a 1, a 0, and a 1. Now that is an ideal world when you have a perfect square wave, but you don't always have a perfect square wave. Sometimes you have some function of that. Closer to our next example here, which is a sine wave, which in this case it can also be seen as when the voltage is in the positive above the x-axis, then that is considered to be a 1, and if it's below, it's a 0. So this sine wave here shows us a 1, a 0, a 1, and a 0. So 4 bits, 1, 0, 1, 0. Now typically, if you have 8 bits, it's referred to as a byte. We can go into the details now, but I just want to show you a little bit further here. Here we have another wave, but this wave isn't as clearly defined as our previous square wave and sine wave. So we have a definite first part of the wave, which is on the plus above the x-axis, and that could be a 1. The second one, where we're going down to a 0, it's not dropping quite as far down as what the plus went up, but it's reasonably close, and you can have a margin of error, and you can decide if it's for, you as the engineer can decide if it's somewhere between 4 and 5 volts, we accept it as being a 1. So in this case, it's possible that it starts off with a 1, and then it drops down, and it's fairly close to being a 1, and we'll accept that as a 1. But once we climb back up again, that next climb over the x-axis is very low. That's not even 2 volts. So that could be considered as it's not a clear 0, and it's not a clear 1. All right. So you can make a decision here what you want to do with it. Do you want to allow a certain level of error or latitude? Like in this case now, we might say, okay, 1.5 is okay. That is also considered a plus. Or is this an error signal? Okay, and it has got to be resent. So another thing that we can look at here is, for instance, when a wave does get sent through, in our original square wave example, the voltage immediately shot up, okay, to, for instance, 5 volts, and then immediately dropped down to 0 volt. It doesn't always work exactly like that due to many factors, and you sometimes have a step between your jump from low to high or high to low, and that actually causes a slight latency. Which can slow things down ever so slightly. Your instructions start becoming a little bit slower and so forth. But that is basically how electronic signals are converted to ones and zeros. So in a typical household, for instance, we, for instance, run on our home electric current run at 50 hertz, which means there are 50 cycles in your wave per second. Your computer is much, much faster. It's in the order of megahertz, etc., and higher. So you will have, for instance, like in our example of the square wave, this 1 0 1 0 1, you'll actually have millions of those ones and noughts in a period, in a space of a second. And literally, if you double your frequency, you'll have double the amount of those zeros and ones, and therefore double the amount of information that can be pushed through the computer. So with all else being equal, the frequency does affect the speed of the computer. You can go too far and you get too much interference, etc. That's when you're really pushing the limits. Some guys doing overclocking and so forth will be aware of that. And of course also the big boys, Intel, AMD and so forth, trying to create better or faster computers. faster RAM, CPUs, motherboards, and so forth. Anyway, where these electric currents or waves have to run through, they're trying to do it as fast as possible with as little error as possible. All right, and that brings us on to what bits are and bytes. Now, like I say, you need 8 bits for 1 byte, okay? And each one of those bits, okay, has got a number assigned to it where it fits in the 8. So let's say out of 8 bits, in other words, on our square wave here again, let's say we've got 6 bits in here, 1, 2, 3, 4, 1, 2, 3, 4, 5 bits, sorry. So we've got 5 bits here. So what it's basically telling us is that each one of those bits, it's not just a 1 or a 0. It depends where in the byte, in the series of 8 bits, where it places. So if it's, for instance, the very first bit, okay, you might want to read up on this on Big Indian and
a little Indian, and this typically relates to the ordering of the bits in a byte or in a word of a computer. Now, with our Intel and AMD chips and so forth, we are running on little Indian, which means something they call the least significant bit is the very rightmost bit, and the most significant bit is the very leftmost bit. And when you start counting, okay, so you're actually counting kind of in reverse. So you start with the rightmost bit, in other words, the least most significant bit, and that is your 2 to the 0, or your first bit, and then you count 2 to the 1, 2 to the, and so you move towards the left.
So that now brings us to the point where we can actually examine how do we actually use these waves, these opposite polarities, magnetic polarities, electric fields, and so forth, to actually represent numbers and so forth that we can actually use. So like I said before, what they've decided to do is to take 8 bits, in other words, 1s and 0s, a +5, a -5, etc., a north or a south pole. These opposites, they've decided to call the one a 1 and the other one a 0, or a true and a false, or whatever, but as long as they are termed in a binary format. Now, we'll be using 1s and 0s, because that's basically what it comes down to when you start dealing with programming. So, as an example here, I've, for instance, got right on top the number, the binary number 001, 4 zeros and a 1. Now, if that, for instance, was a decimal number, so let's forget about the leading zeros on the left, but it was 1 and 4 zeros and a 1. So in other words, 10,001. Okay, or what am I saying? 100,001. All right. The way you would typically calculate that is on top of the last 1. All right, you'll say 10 to the 0, because we are using a decimal system which contains 10 possible characters. So we write down those possible characters, which is 10, and because we're on the first character, we put in a 0. So instead of 1, we say 10 to the 0. 10 to the 0, as we know from our maths, is a 1, and because there's already a 1 there, 1 times 1 is 1. Alright, so that's part of our answer. I know I'm moving a little bit quick over binary here, but the basic idea. Then right after that, you've got 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. Okay, so that's the base, which is 2 to the power of 5. Now, 2 to the power of 5 is 32. Alright? So if you look down the examples I gave you, so if all our bits are 0, that means we're transferring a value of 0. I mean, that's a valid value. You might want to specify how many elephants can fit in a post box. Well, the answer is 0. So that is a valid value you might want to send over a computer bus into a CPU and so forth, or to RAM, etc. Then the very next one is basically it's got a 1 in it at the end. And that means it's 2 to the 0, which is 1. So you take that value, which is 1, times 2 to the 0, so it's 1 times 1
is 1. So if you've got 7 zeros and a 1, the answer is 1. If you've got 6 zeros, however, a 1 and then a 0, making 8 bits in total, it now becomes 2 to the 1, all right, times 1. Okay, so 2 to the 1 is 2, times 1 is 2. So 1 0 equals 2. So you would imagine then that 1 1 would be 3, because yes, it is. It's 2 to the 0, which is 1, times 1, right? This is the first one we're dealing with. 2 to the 0 times 1 is 1. And then we add the next one, which is 2 to the 1 times 1, okay, which is 2. So 2 plus 1 is 3. And you could follow that exact same logic through and reach 65 on the next example. If all of the bits are set, all right, then we have a value of 255. But in truth, you'll often hear people say to you that the maximum number of values that can be stored in an 8-bit byte is 256. Then you're going to say to them, well, that's not possible. It's 255. All right. No, that's when you enable all the ones. But remember, the case where zeros is active is also true. So it's not 255. It's 255 plus all the zeros, which is another one. So it's 256 possible combinations. But the largest physical number you can show is 255. But remember, from 0 to 255 is actually 256 numbers. And you can try any combination there. And this is basically what our ASCII character set uses. It uses, for instance, the first 7 bits. And then you also have ANSI, which moves on to using the 8 bits and a full byte. Then you also have, of course, numbers. I just mentioned that you can specify characters, ASCII characters, and so forth. So, for instance, if I remember correctly, 96 represented as zeros and ones here refers to, I think, capital A. So that's how the computer knows. If you press a key on the keyboard, it gets that 8-bit byte coming through with certain values, one set. It calculates what the number is, and let's say it's 95 or 96, and that means that you're sending an A through to the computer. So as you're typing a letter or programming, you press on A, the A gets sent through to the computer.
So here we have an example of an 8-bit word, which adds up to 143 in decimal. Now you might want a bigger number than the maximum that can fit into an 8-bit, being 255. You might need more bits, and so what you can do is you can add on an additional word, and in other words, use 16 bits to represent a single number. And in this example, we're going up to 32,953. Then, so you can continue with this concept and move up to 32-bit numbers. I mean, I remember I started on 8-bit computers, and then 16-bit, 286s, then 32 bits, and now we're on 64-bit computers. And here we have, for instance, an example of a 64-bit number which uses 8 bytes. And if you'll notice, there's only, in that very long number, there's only 3 ones in there. But you'll, a little bit further down in the middle there, you'll notice the concept remains the same. So you take 2 to the 0, which is 1, all right, and you already have then a 1 in that slot. So it's 1 times 1 is 1. And then you have a 1 in the 2 to 7 slot. So 2 to 7 is 128 times 1. So it's 128 plus 1. And then you also have 206, 2 to the power 61. And you add them all up, and you get this ginormous number. And trust me, a 64-bit number can be multiple times bigger than this. And then you can still go so far as to have 128-bit numbers and 256-bit numbers and 512. It just becomes
huge. It's massive. But really what I'm trying to show you here is the beginnings of how data is sent around inside a computer. You can, for instance, use a single byte to represent characters. So when you're typing your program and you want to type out the word for, F-O-R, then you need to tell the computer to show you on the screen when you click the keyboard the F character. It must take that F character and stick it on the screen and show it as an F. And same with the O and same with the R. And they all have their own unique code or their own number inside of an 8-bit word. You do get other translations of characters, such as the very popular UTF-8. That allows you to use many more characters, but we're not going to go into those details. So, all right, and the whole binary concept is whether communication with your computer, or not with the computer, but the communication of the computer itself, when it's running hardware, software programs. That software program initially has to live somewhere. So let's say you turn your computer on the first time. All right, there is no memory inside your CPU or in your RAM that still lives from when you last turned your computer off. So any programs you were running, any variables you saved into memory, they were all cleared, all right, because the moment you turn the power off, that memory and the CPU registers, which is a form of memory as well, they're called volatile memory, meaning that the information can be lost. So the moment the power gets turned off, that type of memory, volatile memory, loses all its information immediately. Then you get non-volatile memory, which for instance would be your hard drive, a memory stick, well, even a CD-ROM drive for that matter. So where you don't need constant power to make sure that the bits and the bytes stay on the ones and the zeros they should be. If you pull a USB out of your computer, the bits and bytes are still the same where they are. A CD-ROM drive, those bits and bytes are represented by holes and so forth in the CP, in the CD or the DVD. So yeah, so that's non-volatile. So that can last for a much longer period. I mean, sure, wear and tear over the years, over 1,000 years is going to destroy something. But in general, you basically have volatile and non-volatile memory. And you can also think of it as your volatile memory is normally a much faster memory. It's normally much faster than non-volatile. So your volatile memory is basically, if you could pull it from your CPU's memory all the way up to the RAM chips that you buy, your 4 gig, your 8 gig, your 16 gig, 32 gig chips that you have in your computer. The CPU itself has got a very small amount of space where it can store data, which are referred to as registers. These registers have got different meanings, but some of them just holds a little bit of data. It might be a byte, it might be 64 bits, depends on the individual architecture of the CPU. And then it also has what they call cache, secondary cache, or L1 cache, L2 cache. And that's, each one of them is a little bit more memory. It's like normal RAM, but it's much faster and therefore more expensive, and they keep it very close to the CPU, so the CPU has got access to that RAM very quickly and can do calculations and so forth. And so it progresses further, goes beyond different levels of cache RAM, and finally ends up at your main RAM itself, which is the slowest of the volatile RAMs memory. But it's still ridiculously fast when you compare it to things like hard drives, CD-ROM drives, USBs, and so forth. Then obviously the same technique, or the same binary utilization, also accounts for when you send data over a network cable. That is also just bits and bytes that are being sent in the exact same format as what you've discussed here. But yes, okay, so this video definitely went much longer than what I thought it would, but I do think these basics are very, very important. Don't think that the rest of the video is going to be on the same level of technicality when it comes to, you know, binary electronics and that type of stuff. It won't be. We'll be moving more and more into actual development. And like I said, we'll be concentrating mostly on C# development. But most of the principles, well, definitely everything's been discussed so far, and a lot of the principles, you know, when we get to how does variables work, and structures, arrays, and conditional statements and so forth, that is common to all languages, not only C#. All languages follow them. So for, you know, C# specific stuff, it'll be a few videos from now before we get there. So great, thanks a lot, man. Hope you enjoyed it. I hope you learned a little something. Like I say, a little bit stretched out, but maybe a good refresher if you already knew it. Thanks a lot, and I'll catch you on the next one. See you guys, bye.